So in this video we're going to talk about orbital motion. This is part of the IB Diploma Program Physics, Unit 10.2, called Fields at Work. This is a nice application of Newton's laws of gravitation. So let's say we have a system whereby we have a mass m, capital M, and around this mass we have a satellite which is said to be in orbit around the mass. That means it makes a complete circuit without it crashing into the mass or going off into space. So the velocity, the orbital velocity, is just right for this system, for this satellite to be in orbit. And we have a centripetal force acting on the satellite, and we give the satellite mass m. Now we're going to try and work out an expression for the orbital speed of this satellite. Well, we're going to do this by working out the total energy of the system. So we can ask ourselves the question, what energy does it have? Well, we know that for something moving it must have kinetic energy equal to 1/2 mv squared. We also know that something that's in a gravitational field must have gravitational potential energy, which is given by minus big G big M little m over r, where r is the distance between the centres of the objects. Notice the minus sign here. So the total energy is simply 1/2 mv squared minus G big M little m over r. Now we also know from Newton's second law that this force here is the centripetal force, can be given by mv squared over r. And what force is it that's giving rise to this centripetal force? Well, it's the gravitational force, the pull on the satellite due to the planet, or the whatever this big object is here. Could be a star, could be a planet. And that's given by big G big M little m over r squared. So if we equate these two, we get mv squared over r, big G, big M, little m over r squared. One of the r's cancels, little m cancels, and we end up with v squared equals big G, big M over r. And this v is in fact the orbital speed. So if we square root all this thing, we get the orbital speed, which is not dependent on the mass of the satellite, interestingly enough. Let's take a new slide. Now notice we worked out an expression for the total energy before, which was half mv squared minus G big M little m over r. Now this v here was the orbital speed, which I have derived from the previous slide. It was big G big M over r. So if I substitute this thing into here, I get a half little m times big G M over r minus big G big M little m over r. Turns out that this is, if we just move this thing here is exactly half of this. So simplifying just gives me half of big G big M little m over r. Now it turns out, knowing this, that if you were to fire an object off the surface of the planet with different speeds, then you give you some different possibilities. Let's have our planet here. So if we had a positive total energy, and I fired off this object from the surface of my planet, then it would end up leaving the pull of the object and never return. It would follow a path which is called a hyperbola. If I gave it enough energy so that the energy I gave it was equal to the total energy, the total energy of the object is 0, then it also ends up leaving the gravitational pull, and at infinity it will just stop. However, if I gave my satellite if the total energy that I gave it is negative, then it will end up in orbit either in a circular or elliptical orbit. And there are some simulations you can do to play around with this and actually test this for yourself. Like this one I found here. I'll include the link in the comments, but here we go. We can have Earth here, and I can fire it off, and at this particular total energy of the system, it forms an elliptical orbit here.